Here we're going to go through the electric field due to various charge distributions. We're going to take a few videos to do this. This is our first one. So let's see what we're up against. If we have a distributed charge instead of a point charge, then we have to break the distributed charge Q into a bunch of tiny dq elements, each of which is at a different r distance from the point that we're interested in, and each of which then will contribute a tiny dE element, I might put a vector over that, to the total electric field. Then we have to add up vectorially, that is a real word actually, all of the dEs. And we usually have to do that using calculus. Sometimes, we might say often, we are aided by symmetry of the charge distribution. So that sounds rather complicated, which is why we're going to go through it in several videos, but I hopefully will be able to convey to you that maybe it's not as bad as you might have feared. So here we have a uniform rod. When we say uniform, what that means is that this charge is uniformly distributed along this entire rod. Here we have a point in space. There's no charge here. This is just some point. There's nothing there, actually. I've just put a dot there to give us something to focus on. And we want to know, what's the electric field at this point? Well, first, what's its direction? Let's give a qualitative description. And the answer is the electric field at point P points to the left, doesn't it? That is one part of our answer there. The electric field points to the left, and we know that because electric field lines are directed away from positive charges, so the electric field is definitely pointing to the left here. Now we need to find its magnitude. And so to find the magnitude of this, what we have to do is, there are, you see in this rod, a bunch of tiny little dq elements. All right, let me label one of those right there. That little fella right there. It's so tiny that, of course, we can't even see it, but I'll just label one of them right there. And you can see that he is a distance r away from point P, and therefore he contributes a little dE, a little electric field. However, the dq here, or here, or here, or here, or here, they have a different dE magnitude that they contribute. So what we have to do is we have to take into account each one of those and then add them up. And this is where calculus comes in. So what we're going to do is we're going to do this. We're going to say that the magnitude of the electric field is going to be the sum of all of the little electric fields generated by the dq's, and the limits of that integration are going to be from r equals a. That's where we're going to start. And then eventually, you see, r is going to stretch all the way to here, which is a plus L. So that's going to be what's up above here, a plus L. Now, E, we said in a recent video, is kq over r squared. So what we need to do here, dE then would be k dq over r squared. And again, the limits of that integration are going to be from a to a plus L. Now, the problem here is that this differential, dq, and these limits have to be speaking the same language. And that is not the case here. This is a charge. This dq is an amount of charge. And a plus L and a, those are units of distance or length. So they're not speaking the same language. So what we need to do is, this dq needs to be changed out. And how do we do that? Well, what we need to do is we need to set up a proportion. And here it is. If you look at this diagram here, this dq, obviously it's much smaller than this, but I'll draw it in. That dq has a little thickness, dr. He's got a tiny length. dr is that little amount right there. And the ratio of dq to dr, because this is a uniform rod, that ratio is an equality. dq compared to dr is the same amount as q compared to L. Therefore, dq, you see, is equal to q divided by L times dr. So that's what we're going to put in here. We're going to put our integral sign. We're going to go a there. We're going to go a plus L there. We're going to put our k, and instead of dq, we're going to put q over L times dr. Q over L times dr. And then we don't want to forget our r squared there. So where does this leave us? K, Q, and L are constants. So we can pull those out of the integral. Let me do that down here. KQ over L. And we're going to integrate from A to A plus L. This is r to the minus 2 dr. So what does that give us? KQ over L. Raise that up to the higher power. Divide by that new power. So there's going to be, in effect, a negative sign in there. And we're going to take our limits from A to A plus L. All right, well, what does that give us? That means we're going to put A plus L in there, and then we're going to go A in there. And one little trick here, if you have a negative r to the minus 1, you can basically flip those limits. And in essence, what you get is KQ over L, 1 over A, minus 1 over A plus L. It's a little bit complicated, but that's how it works out.